Internal loadings. Here are our learning outcomes. To show how to use the method of sections for determining the internal loadings in a member, and understand how internal forces develop within a structural element under external loads. Introduction to solid mechanics. Solid mechanics, or mechanics of materials, is the study of internal effects of strain and stress in a solid body subjected to external loadings. Stress is related to the strength of the material. Strain is the measure of deformation, and this is important because it forms the basis for engineering design in machines and structures. So here's a diagram of a beam. By using the method of sections, we take a section cut at point A, which reveals the internal forces at point A. This includes the shear force, the normal force, and the moment. Internal resultant loadings. So imagine you have a beam holding up a structure. We see external forces acting on it, but what's happening inside the beams? To analyze this, we use the method of sections. Recall that the method of sections includes the following steps. 1. We cut the beam at a point of interest. 2. We analyze one half of the beam using a free body diagram. And 3rd, the forces at the cut represent how the beam resists the load. So cutting through a structure exposes the internal forces and moments that keep the system in equilibrium. So these internal forces include the normal force, which pushes or pulls along the beam's length, the shear force, which tries to slide one part over another, and the moment, which describes the turning effect of a force around a fixed point. So in 3 dimensions, we break down forces into components. So axial forces, which act along the axis, shear forces, which act parallel to the surface, and moments, which results from external loads causing bending about an axis. Note that it's important to use the positive sign convention in internal loadings, which is crucial for maintaining consistency, clarity, and accuracy in structural analysis. For axial force, tension is usually considered positive, pulling apart, and compressive is negative, pushing together. For shear forces, a positive convention typically follows the right-hand rule, ensuring consistency across diagrams. Procedure for analysis. To analyze internal loadings, follow the following steps. Identify support reactions, so draw a free body diagram of the entire structure and solve for reactions using equilibrium equations. Make a cut, so the method of sections. Choose a section where internal forces need to be determined. 3rd, draw a free body diagram. Show all applied loads and internal forces at the cut. 4, apply the equilibrium equations. So the summation of forces is equal to 0, which solve for the normal and shear forces, and the summation of moments, which solve for the internal moments. So now let's get into our example. The 500 kilogram engine is suspended from the cane boom in the figure. Determine the resultant internal loadings acting on the cross-section of the boom at point E. So first let's start with our support reactions. Here we will consider the segment AE of the boom, so we must first determine the pin reactions at A. Since member CD is a two-force member, it acts like a cable and therefore exerts a force of FCD, having a known direction. The free body diagram of the boom is shown as such. So first we're going to start by solving for the theta angle by point C. Next we're going to take the summation of moments about point A, which solves for our two-force member of the force in CD. So by looking at the diagram, we can see that the force of CD causes a counterclockwise moment, and the force of the engine causes a clockwise moment about point A. So the force in member CD is equal to 24,524.9 newtons. Next, we take the summation of forces in the x direction, which gives us a value for AX. So the force in the x direction at point A is equal to 19,619.8 newtons. Lastly, we take the summation of forces in the y direction, which yields a solution to the force in the y direction at point A, which is equal to negative 9,809.9 newtons. Next, the free body diagram of segment AE is shown. So we're taking a section cut at E to expose the internal forces that act at point E. Using the equations of equilibrium, we can now solve for the normal force, the shear force, and the moment at point E. So the normal force at point E is equal to 19,619.8 newtons. The shear force at point E is equal to 9,809.9 newtons, and the moment at point E is equal to 9,809.9 newtons. In summary, we solved for the forces in member CD, and we also solved for the reaction forces at point A, which is AX and AY. Using this information, we were able to cut the beam into segment AE and solve for the internal loading forces of NE, VE, and the moment at point E.